Welcome to lecture number 17 of our course on high performance computing. We are currently looking at that functionality of the operating system which we are going to call process management. It relates to how the operating system shares the CPU time of a computer system among the many programs in execution. Now, in the previous lecture we had ended the lecture by trying to put down our thoughts about a good perspective on how to view what a process is. We did this by using adjectives to contrast a process from the program that it may have come from. And we came up with the idea that processes are active entities which change state with time, and that when a process is in the condition of being on the CPU and executing instructions, we could refer to that process as being running. Right? Just as in the sense that and we'll look into this concept a little bit more. So, this concept of a running process. So, you'll recall that what we have said is when a process is in the CPU and its instructions are being executed, then it is changing its state. It is changing the state of its variables, it is changing the state of text, data, stack, heap, maybe not text, but data, stack and heap, registers, page tables, etc. Okay, now, the question which immediately arises is, can two processes be in that condition at the same time? In other words, can two processes be running at the same time? I am using the word running in the sense we have defined it in the previous slide. It is a technical term. A process is in the state running if it is in the CPU and it is causing the execution of instructions through which its different data associated with it may get modified. Now, the answer to this question should be fairly obvious. We have talked about this before. The answer is that no, it clearly cannot be the case. You cannot have two processes running if your system has only one program counter, one instruction register and one set of general purpose registers. Because for a process to be running, it has to be in a condition where its instructions are being executed. And if my computer system has only one program counter, one instruction register and one set of general purpose registers, then only one process can be running at a time. Later on we may learn about computer systems which have more than one program counter, etc. But for the moment our picture of a computer system is one where there is one CPU, and in that one CPU there is one set of special purpose registers and one set of general purpose registers. Therefore, the answer to the question is a definitive no. I cannot have two processes running at the same time. There can be at most one process running at a time. Okay, so the answer is that, as we said, for the kinds of CPUs that we have been talking about so far, there can be only at most one process running at a time. In other words, going back to that hypothetical situation which I often use, that there are 100 processes on a computer system, then if only one of them can be running, let us assume that the process which is running is process P1. That raises the question of what are the other 99 processes doing? What is their condition? What is their state? So, at this point we seem to be talking about running as being the condition of process P1. We can think of running as being the state or the condition in which process P1 is, and we are asking the question, what is the state of the other 99 processes, given that there are 100 processes on the system. Up to this point in time we have seen only one state a process could be in, the state of being in the CPU, its instructions executing, its data changing. So, we need to learn about other states that a process could be in. So, what are some other possible process states? That is what we need to get a handle on next. Okay, now one thing which we have seen is that a process could be waiting for something to happen. And we saw this, for example, in the case of the parent process, which could be sleeping, waiting for its child to terminate. And it could come into this state by executing the wait system call. Right? So, this seems to be another condition that a processor could be in. So, remember, we are going to use the word process state to refer to, at a high level, the condition that a process could be in. So, one possible condition was that a process could be running, but at any given point in time at most one process can be running. What condition could the other processes could be in? And one answer is some of them could be waiting for something to happen, such as a parent process waiting for its child to terminate. And there could be other such situations. So, we will assume that this is a common problem with a common condition that processes could be in. Okay. So, the example of a parent process that made the wait system call and is waiting or sleeping for its child process to terminate. Now, after the child process terminates, what happens? The answer is the parent process may not actually be able to start running right away, because there could be some other process running. And therefore, we need to talk about another state that a process could be in. In other words, another condition that a process could be in, where it is not waiting for anything to happen. On the other hand, it is not running either. So, there is a third possibility, and I will refer to that third possibility. The second possibility was waiting, the first possibility was running, and the third possibility is what I will refer to as ready. So, a process which is not waiting for anything but is not running would be described as being ready. What is it ready for? It is ready to be allowed to run, or it is ready for the operating system to cause it to run. And I am laying the blame at the door of the operating system, since currently we are talking about the different jobs an operating system does for processes, and we are actually talking about the job of sharing CPU time or managing processes, and therefore we understand that this is a responsibility of the operating system, not of the individual user program or of the user. So, in short, this is a possible third state, a state where a process is not waiting, it is not running, but it is essentially ready to be running, and is just a question of the operating system allowing it or causing it to run. In short, we could talk about three possible states or conditions that a process could be in, and I will refer to these three possible conditions as running, waiting, and ready. Ready to run, waiting for something to happen, and running on the CPU. That might be a more complete way to look at it. Ready to be allowed to run by the operating system. Okay. So, there are these three possible states we could think of. Now, before I proceed, I have been talking about the idea that at most one process could be running at a time. Therefore, it is possible that at some points in time there are no processes running, in which case that is something that we need to also think about later. But for the moment, we will assume that there would be one process running, some number of processes waiting, and some number of processes ready. Okay, so the operating system job of managing all these processes is what we know as process management. And from the perspective of the operating system developer, the one kind of question which might arise is this question. This is an operating system design question, but we will ask the question and look at the kinds of ways that operating systems answer this question in order to understand what may happen to the programs that we execute. The question is, what should the operating system do when a process does something that will involve a long time? Okay, now I do need to explain what I mean by a long time. So, let me give you an example. Now, let us suppose that a process does something which results in a hard disk access. What are the different things we have seen that a process could do that would result in a hard disk access? The answer is it might be a read or write operation on a file if the hard disk is implemented if the file is implemented on a hard disk. We have also seen that a process may make a memory reference which results in a page fault, which may also result in a hard disk access. And why do I associate a long time with a hard disk access? Because in the previous lecture, when we were talking about the speed disparity between the main memory and the hard disk, we actually got this ballpark, this approximate idea that the hard disk could be 10 to the 4 times slower than memory. So, if memory is operating in terms of hundreds of nanoseconds or 100 nanoseconds, the hard disk is operating in terms of milliseconds or thereabouts, possibly even larger than milliseconds. Therefore, the hard disk is substantially slower than the main memory, and if you want to compare the hard disk with CPU, the situation is much worse. So, the question is a relevant question, because if a process does some operation which results in a disk operation, a disk access being required, and if the processor waits for the disk operation to complete, in other words, if the processor does nothing while the disk operation is going on, then from the processor's perspective, this is going to take billions of cycles. Remember, the processor is 2 orders of magnitude faster, substantially faster than the Let me just explain where this billions came from. We know that the processor is operating on a nanosecond time scale, and we know that the hard disk, rather than being milliseconds, could even be operating on a scale of seconds. I said that in the worst case, a disk operation could take a significant part of a second, and this is where the billions of cycles comes from. Right? There's a difference of 10 to the power of 9 between these two numbers. The 10 to the power 4 was coming from a different calculation. So when a process executes an operation, like a load word which results in a page fault, the net result could be a disk operation, and if the operating system just allows the process to wait for the disk operation to complete, then that would take the equivalent of billions of cycles of processor time. In other words, if the operating system does nothing, then the processor will be idle for billions of cycles. Billion is 10 to the power of 9. Because a processor is operating on a time scale of nanosecond and might be able to finish the execution of one instruction in a nanosecond. Right? So in effect, by doing nothing, by just allowing the process which is waiting for the disk operation to complete, the operating system is causing the processor to idle instead of executing what may have been billions of instructions. Right? So this seems to be a wasteful perspective on how to answer the question. If the operating system had done something different, then conceivably the processor could have been busy doing something useful rather than just waiting for the disk operation to complete. Okay? So from the perspective of this problem, of the question which I have just raised, the question was, what should the operating system do if a process does an operation that takes a long time, such as a disk operation? The operating system should probably be designed so that it tries to maximize processor utilization. This is one consideration that could be taken into account in designing the different strategies inside the operating system. What do I mean by utilization? By utilization I mean the fraction of time that the processor is busy. So if the operating system is able to make sure that the processor is fetching and decoding and executing instructions 100% of the time, then conceivably it will be much more effective in reducing the delays that users see and making programs run much faster. Therefore, maximizing the processor utilization, percentage of time that the processor is busy, trying to get it as close to 100% or a fraction of 1.0. Utilization will often be described as a percentage by multiplying the fraction by 100. This would be a good objective for an operating system to have. But it is possible that other objectives might also come into play. Now, before we think about that, how could the operating system cause the utilization of the processor to increase in the event that we had just talked about, where one process does an operation which results in a long operation like a disk access? The answer is, the operating system could actually change the status of that process which was running into the state waiting, and it could make some other process the running process. So as soon as that disk operation happened, if the operating system had changed the status of the then running process to waiting and had made one of the ready processes running, then the running process could have executed potentially billions of instructions in the time that the disk operation took place, and the net result would have been that the utilization of the processor, the fraction of time that the processor is busy, would have been close to this 100% objective. So this seems like a good thing for an operating system to try to do. Try to maximize utilization, possibly by switching from a process which should be waiting to a process that is ready, so that the process which was ready can now run and progress, execute instructions, thereby progressing towards its own termination and also improving the processor utilization. So the processor utilization is some kind of a indication of how successful programs are as a whole. Okay, now in this particular suggestion, it was indicated that the operating system could make another process into the running process, and that raises the question of which other process might the operating system pick. Right? So when a process is running and does a long operation, it would be made into a waiting process, which is fairly clear. But the question is, which process should be made into a running process, into the running process? Now this decision is something which is built into a part of the operating system called the process scheduler. Since the process scheduler does the activity of scheduling processes to the CPU Right? It makes decisions about when a particular process should be allowed to run on the CPU, hence the name scheduler. Just like you have a scheduler in the bus station to decide when buses should depart, you have a scheduler in the operating system to decide when processes should be allowed to run. So let's talk about the specifics of process management in terms of what a process scheduler might do. Right, so I'll talk of the process scheduler as being the part of the operating system that manages the sharing of CPU time among the processes which are on the system. Now, what possible considerations could the scheduler make in making scheduling decisions? The scheduling decisions relate to the decision of which other process should be allowed to run. That is essentially the scheduling decision. Okay, now one consideration which might be used is trying to minimize the average program execution time. So on a particular system, if I have, let's say, 3 programs in execution, and they may be running as 6 processes, then the idea here is each of these programs started at some point in time and it's going to finish at some point in time. So I have some idea about how much time that program ultimately takes. Similarly, some idea about how much time the second program ultimately takes, and some information about how much time the third program actually takes. I will know all these times after the programs have all finished execution. So then I could add them up and divide by 3, and that's what I mean by the average program execution time. So this would seem to be a reasonable idea in the sense that if there are many programs in execution, if the alternative would have been that the operating system might try to do things, make scheduling decisions based on the well-being of one program, whereas here we're talking about making scheduling decisions based on the average well-being of all the programs by trying to minimize the average program execution time. So this does not seem to be too biased towards any one program, and it does make sense in terms of a strategy, the basis for building strategies that could be incorporated into the operating system scheduler. Okay, now unfortunately, if one does this, there is no guarantee that one program may not get treated extremely badly at the expense of some other programs getting treated very well and the average coming down. Therefore, an additional consideration that might be used is to also ensure that there is fairness to all the programs in execution. One does not want to sacrifice 1 or 2 processes in the interests of the average value. So minimizing average program execution time does not actually guarantee fairness. So this turns out to be another consideration that should be taken into account by a process scheduler. And we'll relate to this in a few seconds. So in essence, we're talking about a part of the operating system. The person who designs the operating system is going to have to design strategies, and these are considerations which might be used in designing strategies. When we talked about memory management, for example, we talked about the problem of how the page fault handler could determine which page to replace. So that was the problem. It had to make decisions about which page to replace, and the strategy in that case was built upon the consideration of principle of locality of reference, and ended up in a policy called least recently used. Right? So we're going to run along the same lines here. Here we have a problem. We have some kind of a strategy, which hopefully will boil down into some kind of policies, which can then be implemented inside the process scheduler. Okay, now there are many possible scheduling policies that have been considered. Let me start with some basic concepts so that you will realize in different systems that you might encounter, some or the other may show up. Okay, now one possible idea that could be used is we could let the currently running process continue to run. Remember, running is a condition that a process is in. A running process is the one which is in the CPU, its instructions are being executed, it is changing in its state. So one overall strategy that an operating system process scheduler could have is forget about waiting for a disk event. You could just have the strategy of let the currently running process continue to do so until it does something that involves a long time. So until the thing like the disk access happens, let the currently running process continue to do so. This is one higher level strategy that an operating system based process scheduler might use. So it is going to take into account the problem with the disk access that we talked about, but until that problem arises, it just lets the currently running process continue. Now any process scheduling policy which uses this idea when the long event does happen, it would switch the currently running process into the state waiting, as we saw, and would switch one of the ready processes. In other words, among all the processes which are ready to run on the processor, it would pick one of them and make that into the running process. That's what I mean by switching to one of the ready processes. What this means is that it would make one of the ready processes into the new running process. So the old running process would become the waiting process, and one of the ready processes would become the new running process in the event of the long wait time. Now, what if the currently running process does not execute a long wait delay? What if it does not execute an instruction which causes a page fault, or it does not do a disk I/O? Then there is a danger that the currently running process could keep running indefinitely, and this may not be good for the other processes. So that's the one weakness of this idea 1. Just to highlight how dangerous idea 1 could be, consider the situation which I outline over here. So I have a currently running process, and it's in a situation where it's going to be guaranteed that it can continue to be currently running as long as it does not do a operation which takes a long time. In other words, it does not do a disk operation or does not suffer a page fault. Now, what if the currently running process is a process which is executing an infinite loop? First of all, what do I mean by an infinite loop? By infinite loop, I mean a loop which continues indefinitely. For example, in here I'm showing you a very simple, the simplest possible C infinite loop. It is a loop in which it has a condition which is always true, and there's no statements inside the loop, so it just continues looping forever and ever. This kind of a loop is not going to suffer from page faults. It does not, since it does not make memory accesses. It's not doing any file I/O, and therefore it's not going to involve any long operation. It's just going to execute forever and ever and ever, which is why it's called an infinite loop. And over here I comment that as a simple infinite loop. So this is clearly a malevolent program. It was written with the intent of just running indefinitely. But if there was such a program running as a process on the system and it became the running process, then this process under idea 1 would never give up the CPU, and therefore no other process would have any opportunity of running on the system. No other process would have any opportunity of running on the system if the process scheduler used this idea. Okay, now what this really means is that for systems, for operating systems which are going to be used in situations where real users are involved, cannot use this idea. This is an extremely dangerous idea, because any user who wanted to could just write a program which has an infinite loop just for the fun of it, maybe just to see if he can cause the whole system to become useless. And the net effect would be that no other process running on the system would make any progress. No other programs would complete. His infinite loop would run indefinitely. So that would be malevolent behavior, an attempt to sabotage the system. But there are situations where this kind of an infinite loop may happen without malevolent intentions. For example, when you are debugging a program, it's conceivable that before the program reaches its correct state, it may contain situations which you had not anticipated, as a result of which there may be infinite loops within the program. And if you left your program overnight to run because for some reason or the other, during the time that you were away, no other process would be able to make any progress if the operating system had used idea 1. So even if it's not malevolent, this kind of situation could arise during, for example, process debugging or something of that kind, program debugging. Now this kind of a idea is clearly not good for, as I said, for operating systems that are going to be used by multiple users, as no other process would ever get to run if the operating system uses idea 1. However, this idea is used in certain other scenarios, and in general an operating system process scheduler which uses idea 1 would be referred to as a non-preemptive policy. The alternative that we are going to see is where there is something called preemption, and the operating systems that you typically use preemptive scheduling policies. But to start off with, it would be useful to get an idea about how non-preemptive policies might work. And just to put your mind at rest, a non-preemptive policy would not be used in operating systems like Unix or Linux, but could be used in some restricted environment where it is known that there are no infinite loops, and where the programs are written very carefully so that they give up the CPU possibly by doing long duration events every once in a while, so that other processes can get access to the CPU. For example, in certain embedded systems, such as within a cell phone where different programs may be in execution, this kind of a scheduling policy may in fact make sense. So we should not rule out the idea of a non-preemptive policy. Right? But from the perspective of Unix-like situations where there are multiple users and it looks like a single user, if he knew that the operating system was using a non-preemptive policy and that by writing a program with an infinite loop he could cause havoc and prevent other processes from making any progress, this seems to be a very good example of not being fair. I had used the term fairness, and this would clearly be a situation where a lot of processes are being treated unfairly. They have absolutely no chance of getting CPU time, and therefore one does not associate fairness with the scheduling policy. Fairness would have to be incorporated into systems that use non-preemptive policies by careful encoding of the programs. The programs would have to be responsibly written. Okay, now the alternative, as I said, is that an operating system process scheduler could use something called preemption as opposed to not doing preemption. And the idea of preemption is that the operating system every once in a while preempts the running process from the CPU even though it is not waiting for something. And what we mean by preempts is evicts. We had used the word evicts in connection with page replacement, replacing one page with another page in main memory. Here we have a similar kind of a concept. One process is being evicted from the CPU in favor of another process, and that's what the word preempt is being used for here. So in a preemptive process scheduling policy, the operating system will preempt or evict the running process from the CPU even though it is not waiting for something, even though it is not doing a long duration event, for example. And this is clearly being done in the interests of either improving the average program execution time or in terms of improving the fairness to the other processes on the system. So we expect that Unix and Linux systems we are going to find this kind of preemptive policy. Now the question which may arise is, when does the operating system preempt a process? And the idea is that an idea which is often used is that in a preemptive scenario, the operating system might give a process some maximum amount of CPU time and then preempt it. And the reason for preempting it is to give some benefit to the other processes which are ready on that system. Now the term CPU time slice is often used for that maximum amount of CPU time. So for example, if you are told that the CPU time slice on your Linux system is 1 second, then you would take that to mean that after a process has been running for 1 second, the operating system will preempt it. It will move that process into the ready state and cause one of the ready processes to become the currently running process. And by doing this, other processes are getting some CPU time, and this will keep the behavior of the sharing of the CPU time resource a little bit fairer. So this concept of the CPU time slice, which is the maximum amount of time that a process will get before it is preempted or evicted from the CPU by the operating system. Why do I use the term maximum amount of time? I use the term maximum amount of time because it is possible that before this 1 second has elapsed, the process may do an operation which causes it to delay. It may do an operation such as a file I/O or may suffer a page fault, as a result of which the operating system may have switched it out because it was waiting for a long duration event anyway. So that's why I use the term maximum amount of time. This 1 second is the maximum amount of time a process could get, and it will get this 1 second only if it does not cause the operating system to remove it from the CPU for some other reason, such as doing a long duration event possibly relating to a disk operation. Okay, now with this quick introduction to how a process scheduler might work, we can get an overall picture of what's happening behind the scenes from the perspective of the process by something called a process state transition diagram. So we know that there are 3 process states that we have been talking about. They are running, ready, and waiting. And in this diagram, we are going to try to show the conditions under which a process which is in one of these states could move into another one of the states. And this kind of process state transition diagrams are useful to get an overall perspective of what the operating system is doing. So when you look at a process state transition diagram, you will see many arcs. So this is an arc going from the running state to the ready state. and it is labeled. In this particular arc is labeled preempted or yields the CPU, and this is going from the running state to the ready state. So what this means is, if there was a process which was in the running state and it was preempted, in other words the operating system forcibly evicts it from the CPU, then that process would move into the ready state. Now it is also possible that there are mechanisms by which a process can voluntarily yield the CPU or give up the CPU. We haven't talked about any such mechanism yet, but let us suppose that there are. Then if there was a process which was in the running state and it voluntarily yields the CPU by using mechanisms available for that purpose, then that process would move into the ready state. It is not waiting for anything to happen, it is ready to actually start running once again. That is why I talk about, that is why we see this arc going from the running state to the ready state. Okay, now under what conditions could a process move from the ready state to the running state? And the answer is, we look at an arc going from the ready state to the running state, and we see that the label on that is scheduled. We have seen the term scheduler. I talked about the operating system process scheduler, and I said that the operating system schedules the processes onto the CPU, and therefore this word scheduled must mean the operating system operation through which a process which is ready is selected to become the running process. Hence the arc going from ready to running is labeled scheduled. A process will move from the ready state to the running state because it is selected by the process scheduler to be the one process from among all the processes which are in ready state to move to the running state and become the one process that is running. Okay, now if we look at the arc going from the running state to the waiting state, we see that it is labeled waiting for an event to happen. So for example, if there is a process which is running and it executes the wait system call, then we know that it is basically wants to sleep until something happens to its child, and in this activity it is waiting for an event to happen, which the event it is waiting to happen is possibly the exit of its child, and therefore that is why this is labeled as waiting for an event to happen, the result of which it goes into the waiting state. It does not go into the ready state because it is not actually ready to run right now. It will be ready to run only when the event that it is waiting for has happened. There could be a similar arc or a similar label which could be put here for a process which does a disk I/O operation, right? The long duration event that we had talked about earlier. So if there is a process which is in the running state and it does a disk I/O operation, then we now learn it will go into the waiting state, and it will be in the waiting state until the disk I/O operation completes. What should happen to the process which is waiting for the disk I/O to complete? Remember, in this case the event that it is waiting for is the completion of the disk input or output operation. So what should happen to the process which is waiting for the disk input or output operation to complete when the disk I/O actually does complete? The answer is, we expect that it should move into the ready state, and therefore we expect to see an arc going from waiting to ready and labeled the awaited event happens, from waiting to ready. Subsequently, that process in the ready state will sooner or later get scheduled at the discretion of the process scheduler. So a diagram like this is very useful. It gives us a good idea about the behavior from the perspective of processes, the behavior that processes can expect in terms of how the operating system process scheduler is sharing the CPU time among all the processes on the system. In practice, you may see process state transition diagrams with many more states. For example, if you looked at the Linux process state transition diagram, it may have a large number of states, and that may relate to certain other conditions which may have to be taken into account, or simply certain special cases that occur. For example, you know that when a process is running, when it executes a fork system call, the effect is that a new process comes into existence, and that conceivably it will take some time for that new process to actually be created, because a lot of activity has to happen to create a new process. Its text, data, stack, heap have to be created, and that involves a lot of memory operations and possibly some disk operations. Therefore, a fork operation is likely to take a fair amount of time. So if the process which is running is doing a fork operation, the new process which comes into existence may come into existence in another state from which it might later on move into the ready state. So, there could well be a state called new process, and it might get entered into because of a fork system call. Similarly, a process which is running and executes the exit system call, we know, essentially wants to terminate gracefully. So, it is conceivable that one might find another state which is labeled, which is known as exiting, and that is entered into from the running state only if the process executes the exit system call. So, this might be labeled exit. So, similarly, there could be other states in a more real world process state transition diagram, but this 3-state process state transition diagram that we have discussed gives us an adequate idea about what is happening behind the scenes in terms of a process being changed from waiting for something to happen to ready to be allowed to run on the CPU to actually being the one process that is running on the CPU with the sequence of events that we went through in this slide. Okay, now let us think a little bit about what is involved in the transition from ready to running, which happens when a process which was ready is scheduled to run. Now, this particular event is often referred to as a context switch, and it is called a context switch because it is what happens when the operating system changes which process is currently running on the CPU. Right, so, if there, I will go back to the previous slide. So, if process P1 was currently running and many processes were currently ready, then when the operating system evicts process P1 may end up as a ready process, and process P4 may end up as a new running process. So, there is a switch from process P1 to P4 as far as the running on the CPU is concerned. That is why this is called a switch. So, when the operating system changes or switches which process is currently running on the CPU, this event is known as a context switch. Now, the thing to note is that context switch may be an event that takes a reasonable amount of time, because what is going to have to happen is that whatever state was present in the hardware, in other words the contents of registers, the contents of program counter, the contents of instruction register prior to the context switch, all related to the old process which used to be running, in other words process P1. And before process P4 can start running on the process, its picture of what should be in the registers and what values should be in the program counter register, and what instruction should be the instruction register must be present in the hardware. Therefore, the context switch must involve replacing the hardware state of the previously running process with that of the newly scheduled process, and only after that has been done can the newly scheduled process actually start changing the values of the registers. Therefore, associated with the context switch, there must be some saving. The operating system must remember or save the hardware state of the process that used to be running, in other words process P1, and it must put into the hardware, into the registers, in other words it must restore the hardware state of the newly scheduled process, in other words P4. So, the context switch will involve these two operations: saving the hardware state of the previously running process and restoring the hardware state of the newly scheduled process. What does this mean? This means that somewhere the operating system must be remembering the hardware context, in other words the hardware state, the contents of all the hardware registers as far as each process is concerned, the perspective of process P1 about what the contents of the registers are, as opposed to the perspective of process P4 as far as the contents of the hardware registers are concerned. When process P1 is evicted from the CPU, it must remember what its perspective of the registers was, and when process P4 is to enter the CPU, it must put into the hardware process P4's perspective of what the hardware registers are supposed to contain. So, where is the operating system supposed to save all this information, the hardware state? You will recall that we had talked about the hardware state, the hardware registers, as being part of the data associated with the process, and therefore the operating system is going to have certain space associated with remembering the hardware state of each process, and this is going to be part of the context or the hardware state of each particular process. So, the operating system is going to manage this in memory, and the saving of the old state and the restoring of the new state are the essential components of what happens during a context switch. And the reason that I say that this could take a reasonable amount of time is that this is clearly going to involve many memory operations, because in the case of a RISC instruction set, each of the register values will have to be loaded from wherever it was stored by the operating system into the corresponding register. And if there are 32 registers and if there are 32 general purpose integer registers and 32 general purpose floating point registers and 20 or 30 special purpose registers, the size of that hardware context could easily be a few hundred words, and therefore it's going to take a few hundred instructions for this context switch to happen. Right? That's not unreasonable. It's not unrealistic for us to expect, which is why I said that the context switch could take some amount of time. So there is a little bit of overhead associated with this aspect of how the operating system is managing the CPU time, but it is something which may be necessary in order to allow a single CPU to be shared by a large number of processes. Okay, so this amount of time that it takes may also be useful for the person designing the operating system in deciding what would be a reasonable CPU time slice value. Remember, we talked about the CPU time slice in a previous slide. It was the maximum amount of CPU time that could be allotted to a process before it is preempted from the CPU. So when we come back to this slide, if I told you that the amount of time to do a context switch is let's say 3 microseconds, and then you are asked to decide how big to make the CPU time slice, you could readily understand that you would clearly not want to make the CPU time slice just 10 or 15 microseconds. Because if you made from the perspective of the CPU, 10 or 15 microseconds is actually a large amount of time, because in 10 or 15 microseconds it can execute thousands, if not more, of instructions. However, from the perspective of overhead, having a CPU time slice of only 10 microseconds would mean that if I looked at the CPU timeline, initially it runs a process for 10 microseconds, then it evicts that process, it takes 3 microseconds to context switch, and then it runs the next process for 10 microseconds, then it takes 3 microseconds to context switch, and so on, which means that out of every 13 microseconds, 3 microseconds are wasted, or are not used for the useful execution of programs. In that sense, I might view it as a waste. It's not actually contributing towards the execution of programs, but is part of the overhead of what the operating system is doing, and could be viewed in some sense as a waste. Therefore, this is a fairly high overhead to pay in terms of 3 microseconds out of every 13 microseconds being used in this operating system overhead. On the other hand, if I actually used a CPU time slice of 1 second, then you would say that 3 microseconds is a fairly small or almost insignificant part of 1 second, and therefore the overhead of context switching becomes small enough relating to the CPU time slice. And therefore, the operating system designer would clearly use the CPU time slice, the context switch time overhead idea, how much it is, in making a decision about what a reasonable CPU time slice would be. This number of 1 second may not be that unrealistic for systems today, as is this rough idea about how long it takes to switch from one process to another. Okay, now with this we can actually look at some specific ideas that are talked about for scheduling policies, just like we talked about LRU, FIFO, random, as specific ideas for how one could do page replacement. I'll give you some ideas about some of the specific process scheduling policies people talk about. For completeness, we'll start off with some non-preemptive scheduling policies. Now, one idea for a non-preemptive scheduling policy is this idea of first come, first served. The idea here is the process which came into existence first could be the one that is allowed to run in the CPU first. Hence the name first come, first served. So to implement this kind of a policy, the operating system would clearly maintain, the operating system scheduler would maintain a queue of ready processes. It's obvious to those of you who know what a queue is, but let me explain what I mean by a queue. A queue is a data structure. We've learned about the stack as a data structure. Now I'm telling you about the queue as a data structure. It's a very well-defined term. The queue as a data structure, other than creation and deletion, has 2 well-defined operations. The 2 operations are insert, which in our context here would be adding a new process to the back of the queue, and delete, which relates to removing the process from the front of the queue. Hence, when you think of a queue, you think of the front and the back. And the way that the first come first served scheduling policy would use a queue is that when the time comes where it has to decide which process to schedule next, in other words which process to execute on the CPU next, it would schedule the process which is at the front of the queue, hence the name front. So when you insert a new process, it goes to the back of the queue, and when you want to take a process out of the queue, you take it from the front of the queue. So a queue is typically denoted like this. It has a front and it has a back. So things go into the back and they come out from the front, just like a queue in principle when you're waiting at a queue in a bus stop or something like that. This is the idea which you would have. So if there's a process P1 in the queue and then a process P2 comes into existence, P2 will be added at the back behind process P1. After this, if P5 comes into existence, it gets added into the queue after P2. At this point, if the currently running process is evicted, then the scheduler, if it's using the first come first serve policy, would take process P1 from the front of the queue and make it the running process. Right? So after P1 has been scheduled to run, the queue would look like this. P2 and P5 would be there, and P1 would be the running process. So here I would use the term ready queue because I'm abbreviating it here. Technically I should write this as ready queue. But the operating system is maintaining the information about all the ready processes in the system in a queue because it is using a first come first serve policy. And this abbreviation of READY queue is often used. So this is a very simple idea, but we've seen that non-preemptive scheduling policies are not too good anyway. So you may ask, what's the problem with this particular scheduling policy? And the answer is that just imagine what happens if process P1 takes a long time to execute, and process P2 has also a huge amount of execution time, but process P5 requires only a small amount of time to execute. Then under the first come first serve policy, the average execution time would actually be fairly high because the execution time for P5 would include the amount of time that it waited in the queue for P2 to finish execution. Therefore, first come first served is not a very good policy, even from the, let alone from the, it's a non-preemptive policy, so it's not very good from the perspective of being fair. It's not even a very good policy from the perspective of average execution time because it doesn't seem to do anything special about processes which have short requirements or small requirements of the CPU. Therefore, another process scheduling policy which is talked about in the context of non-preemptive situations is a scheduling policy which actually tries explicitly to minimize the average program execution time by always scheduling the process which requires the least amount of CPU time. So among all the processes in the ready queue, or among all the ready processes, it tries to identify the process which has the lowest requirement as far as execution time is concerned. In other words, it identifies among all the processes the one which requires the least CPU time in order to finish execution, and it schedules that process. And the net effect is going to be that it's going to have the lowest, this particular policy, which is called shortest process next, abbreviated as SPN, provably has the lowest possible average program execution time. It does of course suffer from a minor problem in that one has to be able to get a good estimate about how much CPU time each process will require, which often makes it infeasible. But if one is able to get good estimates of how much CPU time each process will require, notice the problem here is that this requires looking into the future and is therefore always problematic. But if one can overcome that problem, then shortest process next is a good policy because it has some good properties. But since we are not overly concerned about non-preemptive policies, let's quickly move forward and look at some preemptive scheduling policies. Now, one of the older and easy to understand preemptive scheduling policies is a scheduling policy called round robin. This is often abbreviated as RR. You'll remember that what I mean by a preemptive scheduling policy is that after the running process has received the maximum permissible amount of CPU time, which is defined as the CPU time slice, maybe 1 second, then the operating system will automatically evict it from the CPU in favor of one of the ready processes. So that's the class of scheduling policies we're talking about now, called preemptive scheduling policies. How does round robin work? Okay, now what round robin does is, like the first come first served policy, it maintains a first come first served ready queue. So it maintains a queue along the lines of what we saw for the queue is something with a data structure which has a front and a back. New processes enter at the back, and a process exits from this only from the front. So the round robin policy maintains a first come first serve ready queue. So all the ready processes would be present inside a data structure of this kind, an operating system data structure of this kind. Now remember, this is a preemptive policy, so sooner or later the currently running process will reach the end of its time slice and will have to be evicted on a context switch. So when the currently running process is evicted, what will happen is the scheduler will schedule the process from the front of the ready queue. And what will it do with the currently running process, the process which was just running until the context switch occurred? It will put that previously running process to the end of the ready queue, to the back of the ready queue. Right? So essentially the processes which are in the ready queue, one after the other, will get scheduled, and therefore in some sense we view this as being fair. So it's definitely much fairer than any of the non-preemptive scheduling policies, and we see the beginnings of fairness here, because the general idea is that each process will get one CPU time slice before the next process gets its own one CPU time slice, and a process after having got its CPU time slice enters the queue at the back, and therefore sooner or later it too will later on get its second CPU time slice, and so on. Therefore all the processes one by one will make progress when they get CPU time as and when they are scheduled under this round robin strategy. So definitely much fairer than anything that we have seen up to now, and seems like a good basis for the management of processes on something like a Linux or a Unix system. You'll notice that this particular policy doesn't suffer from the problem that we saw with the first come first serve policy, because even if process P1 requires hours and hours of CPU time, even if process P1 contains an infinite loop, and even if process P2 requires huge amounts of CPU time and process P3 requires a very small CPU time, the most amount of time that process P3 will have to wait before it gets scheduled would be 2 CPU time slices. Therefore there is this element of fairness. No one process is going to get overly unfairly treated due to the scheduling policy. So this turns out to be a very interesting kind of an idea, and this is probably a good time to break with our discussion of preemptive scheduling policies for today. We have not yet reached a point where we see a policy that is actually adequate for the real needs of an actual operating system such as Linux or Unix, but we are almost there. In the next lecture we will actually start by looking at something very similar to the scheduling policy used in a real Unix or Linux system. Today we have actually seen a great deal about the different states that a process could be in. We understand that the operating system manages the CPU time by switching the currently running process. At any given point in time, if there's only one CPU, only one process can be running, but by keeping track of the other processes that are in a condition where they could run, and by periodically switching from the process which is running among the processes which are ready using a process scheduling policy, the operating system is able to keep all the processes in some state of progress and allowing successful completion of processes. We'll stop here for today and move forward to a real world kind of a scheduling policy in the next class. Thank you.